Our next speaker is going to be George Wilson. Most of the people here, I think, know George Wilson. He's one of the earlier OpenZFS and ZFS developers, and he's done a lot of work on performance, on pool allocation, and like various aspects of ZFS. And he probably ninja saved a lot of pools from you guys. So please, everyone, welcome George. George Wilson, who is going to talk about the ZIO pipeline.
Thanks, everyone. So if you don't know me, please come up and say hi. I'm also really interested to get to meet new people, and it's great to have this close-knit community kind of working together. So that's fantastic. Anyway, with regards to this talk, I always find it interesting when I have to go and think about a subsystem that I haven't worked on in a really long time. And then you start realizing, gosh, I don't remember this. Why does it work this way? So a lot of this talk is going to be a little bit like that. I've spent a lot of time in the I/O pipeline over the course of my career with ZFS. And so I'm hoping to answer a lot of the questions for people that have maybe never looked at this. But I'm sure there will still be questions to be answered after this talk. So quick shout out to one of my fellow colleagues in crime and when it comes to ZFS. There was this tweet back in June that I saw, and I was like, that's kind of interesting. Maybe that's reason to have a talk about this at the OpenZFS. So that was the inspiration. Initially, this was going to be the presentation. I was just going to stop here. Yeah. Yes. Exactly. So as Brian mentioned, this is actually in the source base, and he was just kind of letting us all know that, hey, this exists. Maybe we should do something about it. Hopefully, this talk inspires somebody to go do something about it. So first of all, let me just kind of set the stage of where the ZIO pipeline lives and kind of some things about it. It's kind of fascinating. The I/O pipeline, for as small a number of lines of code that exist, is actually extremely dense code and does a lot of things that you might not recognize actually happen in that layer. So as you can see in this diagram, the I/O pipeline kind of sits at the lower area of the stack. So it's actually kind of in an area that we refer to as a SPA and is comprised of a couple other components, and it works very closely with the VDEV layer. So it really is the framework for all I/O that is driven through ZFS. So as you're starting to do things, whether it's read, writes, even ioctls, they're coming through the ZIO pipeline. It's in this layer where we're actually going to do our translations from data virtual addresses to actual physical locations on disk. It doesn't actually handle that completely, and it works very closely with the VDEV layer to do that, but it's instrumental in kind of getting that portion done. It's also here where we do things like any transformations, whether it's checksumming, dedupe, compression. So a lot of the things that you're used to seeing, like zpool, set compression equal LZ4. It's like that gets set in an upper layer and it gets passed down to the ZIO, and it's in this layer where that actually happens. And it's kind of neat because the way that the checksumming and compression code works is it's somewhat pluggable, so we can extend it. So we probably have all seen over the course of years where we've extended and added new checksum algorithms, we've added new compression algorithms. It all happens in here. And there's a bunch of other stuff. So there's quite a lot that happens at this layer, whether it's allocation throttling, selecting how we're going to do ditto blocks and which devices have to do I/O to them, whether or not we can do gang blocks or not, and we'll talk a little bit more about those in a few minutes. So the other thing that I started thinking about is why do we refer to this as a pipeline? People have probably worked on file systems, and I've never really seen pipeline used in like an I/O path. There's like I issue the I/O and it gets done and I'm good. But when you think about like pipelines in kind of a CPU context, the reason that pipelines kind of came about was because we wanted to increase throughput and parallelize some of the activity. So like in this kind of little simple example, we can see that there's like 4 different stages for this particular CPU, and as we drive workload through, we can actually have the CPU doing, staying 100% busy by having 4 different instructions working on different stages. So if you think about the I/O, we can kind of do a similar thing. We can say, well, if we kind of break it up, we have like fetching some data where we actually get this from, the user or the caller. We get whatever data buffer they're sending us. We decode it so we know that we're doing kind of like a read or a write. And we initiate the I/O to the underlying device. And then we get some kind of response. So in a sense, we can kind of break this up into pipeline stages. And what we've done with ZFS is we've done exactly that. They're more intricate than just a 4-stage pipeline, and they differ based on the types that exist. So here are some of the basic pipelines that exist in the ZIO subsystem. We have 2 different types for physical IOs, for doing like physical reads and physical writes. We also have logical reads and logical writes. And then we have kind of this bunch of more specialized pipelines for like freeing claims, which is kind of a very unique thing that happens when we actually do a pool import. ioctl, which is primarily used to kind of flush out the write cache. Rewrite, which is primarily only used by the ZIL. And then these other ones like the null and the root pipelines, which we'll talk about. So let's kind of like see what makes up these different pipelines. So when we're talking about these, we actually have different types of IOs that get associated with them. So we just saw there's all these different pipelines that exist, but then there's 6 different types of IOs that can utilize those pipelines. So we have reads, writes, frees, claims, ioctls, and the special null one. And these different types utilize these task queue pools to do the IOs and move the IO pipeline through the various stages. And I call them task queue pools because they're actually comprised of like 2 different task queues. We have like a normal priority, we have a high priority one, and the number of threads associated with each of those task queues depends on the IO type. So if we're talking about something like writes, we may actually have a lot of issuing task queue threads, and versus something like claim, which may only have 1 task queue thread. And the whole general premise behind the IO pipeline and kind of a guiding principle was that we never burn a thread. We never get to a point where when you're driving through the pipeline that you actually go into a condition variable and block. So whenever we actually get to a point where we have to give up control, we transfer control to something else. So you never have one of these threads that's just sitting there doing nothing, waiting for somebody to wake it up. So here's kind of the way the pipelines work. And I've broken these up to kind of show the differences between logical reads and physical reads. So you can see here that the upper section shows the physical reads. We have these stages which are indicated in red, the ready and done stages. These are our interlock stages, and I'll talk more about what they mean and why we have them. And then we have these green stages where we're actually issuing IOs. So these are all the VDEV communication. This is where we're actually going to be talking to the VDEV layer when we're driving IO through the pipeline. And then the blue stages are kind of computational stages that happen throughout the pipeline. So in this case, when we're looking at physical reads, we can see that we simply it's the ready stage where there really might not be very much done there. We issue the IO to disk. Once it completes, we generate the checksum, and then we call done, which calls the callback and notifies the caller that everything's complete. Logical reads look very similar to physical reads. The only difference is that we insert a new stage, which is called read BP init. And the difference here between the two is that when you're doing a physical write, you're actually writing to a known location. You're writing to a known VDEV, a known offset. But when you're doing a logical read, you're actually passing in a block pointer. And that's why we need to actually do some some different things in this read BP init phase, where we're going to look at the block pointer and determine where do we actually need to do the I/O. The write stages also get more complicated. So here, when we're looking at physical writes and logical writes, we can see that there's a common stage that gets inserted, which is issue async. This is where we are actually going to transfer control from the caller's thread to one of these task queue pools. We're going to just say, do this work on my behalf. So both write pipelines will do that for you. They'll also generate the checksum. The difference here is that we see these orange stages that actually exist in the logical case, where we're going to transform data. So this is where you're going to do that compression, the encryption, the things that you're used to kind of doing as a property when you set that as zpool, they're going to be done in these stages of the pipeline. It's also worth noting where the checksum generate code happens. You'll notice that the transformation and the checksum generate happen after we issue the async stage. It's because we want to make sure that we can fan this work out to as many threads as possible to go compress the data, encrypt it, and then once that's stable and the data has finished transforming, we can actually generate the checksum that we're going to put to disk. The logical also introduces these purple phases, which is the allocation code. This is where we're going to first throttle it down to make sure that we're not overloading a bunch of disks that potentially can't handle the workload, and that's done by the DVA throttle. And then the DVA allocate code is where we're actually going to go and talk to the Metaslab subsystem and say, find me a block where you can actually write this. So in the write pipeline, we see it actually branching out and going and talking to not only the VDEV subsystem, but also the Metaslab subsystem in order to actually complete the write. There's also optional stages that can be inserted. So the pipelines themselves aren't static. They can change. So in this case, if we're dealing with reads, we might have a block pointer that was provided for us that actually is part of a dedupe block, in which case we have to add in the stages that are associated with dedupe. Or it might have been a gang block, in which case we have to do all the transformations associated with gang blocks in order to be able to complete the IOs. And writes have a similar thing. So writes have optional stages for dedupe, where we want to go update the DDT table as part of the write. But we also have this concept of a NOP write, where it's possible that we're actually overwriting the data with the exact same content. So if we're doing that, let's just abort the pipeline early, get a performance win, don't do the allocation, don't do any I/O. So that's what you see here with this optional stage. And then I mentioned there's a couple other special pipelines. There's the null or root, which is the simplest of all pipelines, and it just simply has two stages. It has the ready and done stages, which we refer to as the interlock. The idea behind these is that they create a container for you. So you can imagine that if you're trying to do a bunch of work, but you want to be able to kind of wrap all that work around some kind of root, you would issue your IOs, make your root the top parent IO, and we'll talk about the dependency graph and how that works, and then simply just wait for the root IO to complete. And based on our dependency graph, we know that that means that all the subsystem or all the children IOs would have been done as well. And we'll show an example of how that works. And then the rewrite, which looks very similar to write, but the thing that's removed here are the allocation stages. So it's kind of odd if you think about the fact that we're copy on write. Why do we have the rewrite stage? Because obviously we do copy on write when we do go allocate a new block. Well, there's kind of the main use case here is the ZIL. So the ZIL, because of the way that it's structured, actually breaks out its allocation from the pipeline stage. So it allocates the block separately. So it already has a block in hand and simply just wants to go and write that location once it's actually filled it. And that's the main reason why rewrite is there. There's also a special case that happens where you can transform a write pipeline to a rewrite pipeline in the case of sync to convergence when we're actually trying to finish fleshing out a transaction group. So some other things that happen in the ZIO subsystem that's probably worth noting. gang blocks. I mentioned some stages where you can actually add that in. So if we have a condition where the pool is mostly full or severely fragmented, our only option is to, one, fail the I/O, and oftentimes, by the time it gets to the ZIO, it's like, I have no way to tell anybody that I'm about to fail anything, so that's not really a good idea. The other option is I end up creating gang blocks. And gang blocks are taking and creating constituent smaller blocks, logically putting them together to make a larger allocation. So assume that you have like 128K I/O that you want to do, but you have severe fragmentation or you're mostly out of space. When it gets to the I/O pipeline, we would simply try to allocate that 128K block and find that we can't do it. We can't find a contiguous block anywhere. So we would create this concept of a gang header and gang members. And we break that allocation up into smaller chunks. And we'll keep nesting this all the way to the point where we're allocating simple 512 byte sectors, assuming that even with fragmentation, those allocations will always succeed. So this is a huge penalty if you get to a mode where you're having to do this, because now what used to be one I/O to go get your 128K block now can turn into an entire tree of I/Os as we build up and create all these little constituent blocks, stitch them together, and then pass up the logical data to the caller. But it's a necessary concept in order to be able to ensure that we can use all the space that's on the pool. And it also prevents us from just throwing up our hands and saying, sorry, I couldn't allocate that, so obviously, we have to stop all transactions and not let anything go through. We also have this concept of children types. So when we're going through the pipeline, most often we're dealing with logical children. These are I/Os that were requested by some consumer. So like somebody said, go read this block. That read becomes a logical read. And most often, in our cases, that's coming from the ARC. But sometimes within the pipeline, we have to create these new children to go do work on our behalf. And that's what these other types are for. So when we're doing, say, a logical read, that might turn into, if it's a gang block, for example, it might create some gang children to go read all these little constituent blocks, stitch them together, and then transfer that data to the logical I/O, which will then be returned back to the caller. The two common types that you'll see if you're playing with the pipeline will be VDEV children, which are used to go talk to the physical devices, and logical children types, which are the ones that come from the entry points like ZIO read, ZIO write, and so forth. So I mentioned the dependency graph, and it's actually a very powerful thing within the I/O pipeline. The idea here is that we can create these extremely large I/O chains and ensure that things go out to disk in an ordered fashion, and also be able to have, like something like a container, like a root I/O, where we can get the error status and the completion status of a much larger set of I/Os. So the way that the I/O dependency graph works is that we have concepts for notifications, and which are these two stages of ready and done. These are places where we can actually get notified when an I/O completes that stage. So for example, let's say we have, we're writing out some data, and we've gone through and written the level 0 data, and we're getting ready to do the level 1 block. The level 1 I/O may have started, but we don't want it to actually start doing an I/O and writing to disk until the level 0 blocks have actually made it to disk. Or not necessarily made it to disk, but gotten to a point where they're stable. In other words, they're not going to change anymore. Their content is finalized. They've gone through the compression stages. They've done the transformations. They've actually done their block allocation, and maybe they're on their way to disk. So that's where we can actually have these notifications. We can have an I/O that is currently sitting waiting for to get started, waiting for all its children to actually make it through those initial stages where it's doing data transformation and allocation. And then once it reaches a ready stage, then it notifies the parent, says, hey, I'm ready, so obviously you can start being ready and you can move forward because I'm not going to change the data underneath you. And that's what these notification callbacks are for. There's also these stall points. So when the IOs are going through the pipeline, they may need to stall. The common one that I just mentioned actually happens when you get to write compress. So again, the example of I have some level 0 data that I'm writing to disk, it's gone off, it's actually gone through compression, it's gone through encryption, it's gone through checksum, it's in the process of doing an allocation, so we haven't actually allocated its block pointer yet, and the parent IO, which is going to contain the block pointer that points to that data, now comes to write compress. When it reaches that stage, it has to stall, because it can't actually do its compression, it can't do its own internal modifications until the underlying child IO has actually finished and gotten to the ready stage. And the stalls can be either very coarse-grained or fine-grained, depending on the operation that's taking place. In some cases, you only want to wait for like the VDEV children to complete. That might be what you see in like the VDEV IO done stage, where we issued a bunch of IOs and we simply want to wait to make sure that the IOs are now to disk before we move forward. So the only thing we really care about are the VDEV children. We don't care about logical children. So this is something that you'll see throughout the code and is kind of a subtle thing to note, but is actually a very powerful thing when you're actually consuming and driving the IO pipeline. So here's kind of a dependency graph that we would see and is probably pretty common within ZFS, where we create this root IO, and if you remember, the root pipeline simply just has 2 stages in it. We add these children underneath it, so maybe we add the first row of logical children, and they might be reads or writes, we don't really know. They might actually add some additional logical children underneath them, and maybe at the very bottom we get some VDEV children which are actually doing the physical IO. If we were to issue this and then wait for that root ZIO, when the root ZIO gets notified by the done callback, we're guaranteed that everything underneath it is completed. Likewise, you could actually wait somewhere in the middle, and then you're only waiting for things underneath it to complete. Okay, so that's the light part of the talk. So I wanted to kind of go into this because as I was kind of putting this talk together, I quickly found that it's really hard to kind of represent some of these concepts without looking at code. So what I'm going to start with is kind of looking at what is a ZIO? What is this thing that we've been talking about? How does it actually go through this pipeline? What are some critical things of that structure that allow us to do what we do with it? So here's kind of a small portion of the ZIO structure, and it's actually quite large. If you look at it in a source browser, you'll see there's a lot more than just this. But the things that I wanted to point out are some things that kind of are interesting with it. For example, we have this concept of a bookmark. The bookmark is a small structure that actually tells us which file system we're going to, what file we're operating on, what level of indirection are we in, what block ID are we going to be modifying. So we have this context of exactly what we're trying to do I/O to embedded in the I/O from a ZFS object, kind of model. We also have this properties field. And I mentioned that there's all these things that we do when you write, you either do like a ZFS set some property or zpool set some property. Those get passed down to the ZIO itself, and they're stored in this IO prop. So things like, how many copies do you want of this data? Do we want to create additional copies? What checksumming algorithm do you want to use? What compression algorithm do you want to use? All that gets provided by each ZIO. So this is how we can have one ZIO that's off doing LZ4 compression while another one's doing gzip. And that's all embedded into the ZIO structure. I mentioned the IO types. So these are the different types of IOs. So these are going to be reads, writes, frees, claims, ioctls. The child type, this is going to be whether it's a VDEV type, a VDEV child, a logical child, a gang child. And then we also have these callbacks where we can actually call back to the user that has issued the IO periodically as this IO is going through the chain. So we have places where we can actually call back when you get to the ready stage. That's one of the notification points that I mentioned. So as this I/O gets to the ready stage, it can call back to the consumer and say, hey, I'm just letting you know I'm in the ready stage, and the consumer might do something as a result of that or do nothing. Likewise, the done callback is typically the most common one, where we'll actually return the response, whether it's returning the data or some status, but that's where the consumer will get most of its information. And then embedded in here, we also have what stage we're in of the pipeline and what pipeline are we using. And it's worth noting this pipeline that's referenced here may have changed. We may have started doing a full logical write pipeline, and then now that's been converted to a not write pipeline. So things can change. The other thing I was going to mention is we also maintain the priorities for the I/O, and although not really used and consumed by the I/O pipeline, it is passed down to the VDEV scheduler. There's only one place in the pipeline where we actually look at the priority, and that's when we're dealing with the task queue pools, where we want to determine, do we want to send this as a high priority task queue or a normal priority task queue. The rest of these priorities are actually consumed by the VDEV layer when the ZIO actually ships the I/O to the VDEV layer. Okay, so let's talk about how we create one of these suckers. So here's a very common entry point with ZIO read. And we can see that when we call ZIO read, we want to do a logical read. So we're going to pass in a block pointer. So the picture on the right kind of represents what this block pointer would look like. And it has in there 3 DVAs, which are these VDEV A size offset parameters. So when we actually get that block pointer, we're going to use that to go read the physical location. You'll also notice that this is simply calling another function called ZIO create. All these entry points that are primarily used by callers of the I/O pipeline wrap ZIO create. So ZIO create has a lot more functionality, and they're just simply wrapped for convenience sake. So the thing to note here is this parameter, which is currently null, happens to be the VDEV that we're going to do the I/O to. And we pass it in as null because we're passing in a block pointer, and the block pointer is going to determine where the actual physical device is that I need to talk to. We also pass in the stage where we want to start. So we're saying start in the open stage when you're doing this I/O, and then your pipeline is going to be a read pipeline. The other thing to note is that this thing doesn't actually do any I/O. It just simply returns back this structure. So at this point in time, it seems like we should be going off and doing the read, but we're really not going to do that just yet. We're simply going to create the structure, tell it what its intention is going to be, and then sometime later down the road, somebody better go off and do the actual physical I/O. So how do we start that I/O? So you'll see in the code that many places where we may have called a ZIO read, and then sometime later we'll call one of these 2 start points. Either ZIO wait, where we want to wait for that I/O to go through the entire pipeline, or ZIO no wait. Both of these functions will call a kind of the driver of the pipeline, which is ZIO execute, and we'll talk about what that looks like. The other thing to note here is with ZIO no wait, when you issue that, it's kind of deceiving. You think that it's going to be an asynchronous I/O, but it may not be a synchronous I/O, because it's possible for an I/O to get to a point where it will issue and even return in the same context, because we didn't pass that control to anybody else. Again, remember, certain pipelines have the issue async where they pass control right away, others don't. So keep that in mind when you're utilizing this, because no wait doesn't necessarily mean totally asynchronous. We do, however, add this special call to the ZIO add child here. And the reason for this is that we have to have a way to keep track of true asynchronous I/Os. The case in point here is, let's say you've gone off, you created a bunch of ZIOs, and you went off, you did a ZIO no wait on them, they're off and running, and now you want to export your pool. How do we know when those I/Os are done? because nobody's waiting on them anymore. They're now running asynchronously. So what happens here is the concept of the Godfather I/O. So the Godfather I/O is associated at a pool level, and it becomes the parent of all no-weighted I/Os. And when you go to actually export the pool, we're going to do a ZIO wait on the Godfather I/O. When that Godfather I/O completes, we're guaranteed that all its children have completed. It turns out that the Godfather I/O is a simple ZIO root pipeline. It just has 2 stages, just like we saw in the IO dependency graph. So this is a neat way for us to be able to associate these kind of orphaned IOs and be able to get status from them when we need to. And we do that at the time that we actually export the pool. So here's what ZIO execute does. This is the heart of the IO pipeline and the driver of how things make their way through the pipeline. So it's just a pretty simple function that is simply saying, take the IO, and you're going to keep running and calling into different stages until you get to the done callback, or the done stage. So if you start off and you're not in the done stage, so we started, say, in the open stage, we'll simply increment the IO stage. And when we increment the IO stage, we may actually have to increment multiple levels because not all pipelines have all the stages. So these stages are they're power of 2 numerals. And so we may have to go and skip over a couple of them, do that real quick, find the next stage that actually exists in this pipeline, and then determine, first of all, do I need to switch from the current task queue I'm on to something else? In which case, that happens if, say, you're on the interrupt task queue and you're in the process of trying to do an allocation, for example, where you may have to go off and do a bunch of reads because we want to load in some space maps or something. When that happens, we want to make sure that we switch you back over to the issuing task queue. And that primarily happens because the issuing task queues have a lot more threads than the interrupt task queues. But once you're on the right task queue, you're being handled by the right thread, you'll simply call the ZIO pipeline table function. And you can see based on this stage, these are all the various functions that will get invoked. So when you're trying to figure out, okay, what is this pipeline going to do? Well, I mentioned a stage ZIO read BP init. Well, it would call the ZIO read BP init function. If the stage has, a DVA throttle stage in it, then it calls the ZIO deviate throttle function. All these functions will simply return a ZIO, which says execute this ZIO next when we come through this big cycle, or they'll return back a null, which says, hey, I really want to stop right now. That happens when we hit a stall point. So if we're going through the pipeline and all of a sudden we have to wait for a child and that child isn't done, we'll return back a null point back to the ZIO execute function, and it will actually short circuit and break out right here. That's a point where the IO itself is requesting the pipeline to stop. We don't go into a CV wait, we just simply transfer control to somebody else. Okay, so let's look at more examples of how this happens. So here's a case where we're calling ZIO write, and we're calling this from the ARC. So pretty straightforward. The ARC's going to get some information, and then we're going to call ZIO write, and we're going to return back the ZIO. Again, what do we expect to happen here? Absolutely nothing. All we have done is created a structure. We have not actually issued the IO. It turns out write is one of the more complicated cases because what it's trying to do is it's trying to build up the thing we refer to as the mega ZIO. I don't know if this is anywhere in the code, but it is just something that we started calling a long time ago when I think when Mark redid the way that the IO dependency graph works. But we refer to it as the mega ZIO. And the reason for that is this thing can be tens of thousands of IOs. I mean, I don't know if it reaches 100,000 IOs, but it's huge. This happens when we're syncing out and pushing out a transaction group. And so this is how it works. So we started off here. We said, oh, okay, the consumer of ZIO write was actually ARC write. I gave back a ZIO, but I didn't issue it. So, okay, let's go figure out who is going to issue it. Well, the caller of ARC write happens to be debuff write. Well, debuff write simply takes that IO that I returned from the ARC and assigns it to this DRZIO member. Doesn't actually issue it. Okay, well, that's kind of interesting. So let's look at the caller of debuff write. There's actually a couple callers of debuff write, and I'm only showing one here. But in this case, we see that debuff write gets called. We pass in the ZIO, or we take the ZIO that was actually part of the dirty record, and then eventually we're going to call ZIO no wait on it. So we're going to issue it asynchronously. We're not going to wait for it to complete. What's interesting here is this recursive call to debuff sync list. Debuff sync list actually is where debuff sync indirect gets called. What this is going to do is it's going to start looking at all the dirty records and go from the highest level of indirection, create all the ZIOs for those indirect objects, go to the next level, create all the ZIOs, work its way all the way down to the data blocks. So, and every single time it's doing this, we'll notice that it passes in a ZIO, which happens to be the parent, to ARC write. That ZIO gets passed in as the parent to ZIO write. This has now built up that dependency tree that is similar to the example, my example, much smaller than the real mega ZIO. But we build up this huge dependency tree where at the very bottom are all the data blocks, indirect blocks, going all the way up, all the way up to our the meta D node. The other thing that we'll note is we build this thing recursively, and it's when we start actually popping off from the recursion that we start issuing the IOs. So although I don't show it here, there's another function called debuff sync leaf, which is going to sync out all the data blocks. It's going to be the first one to actually start issuing ZIO no waits. So it's going to say, ship off all the data blocks. Then we're going to return from this function. We return back from debuff sync list, and now we ship off the ZIOs associated with the first level of indirection. Return back again, now the second level of indirection. So you get a ton of IOs in flight, but they're all ordered when we ship them out. So when it's coming through the pipeline, you're going to have all these IOs coming through. The first data blocks are going to come through here. They're going to go async. So immediately they're going to hit. This is being issued from typically the SPA sync thread. I think, Matt, we have now one thread per data set. So there's some level of parallelism that happens here, and then we simply take that, we'll parallelize it some more, and then those data blocks will go through the compression, encryption, generate, checksum, go allocate a block, go to the ready stage. Now they don't have to block because they don't have any children, so they're going to keep going. But at the ready stage, they're going to be able to notify the level 1 indirection, hey, I've reached ready stage, which means now the level 1 blocks can start going through this front part of the phase, of the pipeline. So level 1 blocks can start going through and getting to that point. The data blocks will continue, they'll go out to disk, and then they'll contact done. At that point in time, they're again notifying their parent and letting them continue, because they'll get to a stage where we want to make sure that things get completed in a certain order. It's also worth noting here that I mentioned how like DVA allocate contacts the Metaslab code. This is where we're going to go do our copy on write. The VDEV layer here is going to contact one of these functions. And chances are it's going to contact more than one of these functions. So we have this kind of little nuance of every single time we do an I/O, no matter what your pool configuration is, we always call VDEV mirror I/O start. And the reason for this is that we're trying to figure out if we have the copies properties or a ditto block associated with that I/O. And we treat that as a mirror. So rather than kind of doing some special case for like ditto blocks or copies, we just use the mirroring code and hijack that and treat those IOs as mirrors. So you'll always see a call to VDEV mirror IO start. If you really do have mirrors, you might see a call to VDEV mirror IO start twice, and then eventually it calls VDEV disk IO start to actually do the physical IO to the constituents of that mirror. So let's look at that. So here's the allocate path. The allocate path will simply call metaslab alloc. It'll request the allocation that's associated with this IO. If that fails, this is where we're going to call the gang code. So when we have a failure, we'll call ZIO write gang block. ZIO write gang block will create gang children to go do this write again with smaller allocation units. So let's say we get through the allocation code just fine. Now we get to IO start. This is that kind of subtle little piece of code where it says, I go through here, if the VDEV is null, call the mirror operations to do an IO start. Every single time our logical IO comes through here, the logical IO's VDEV is going to be null. So it's going to always call VDEV mirror IO start to try to deal with the copies property and ditto blocks. In the mirror IO start code is where it will also have special logic, which I don't show here, also has special logic if the VDEV is null, and then says, take the block pointer that was allocated, go figure out the VDEVs associated with it, and create this mirror map for me. This mirror map will simply just do this while loop and say, for each one of the children in this mirror map, so let's say we have 2 DVAs, so we'll create 2 children because they're probably going to 2 different VDEVs. I'm going to create a VDEV child IO that's going to go towards child number 1 and child number 2. So for ditto blocks, it looks like mirroring. If you have mirroring, it'll look the same way. So this is what the child IO, this is another part of the pipeline that has a kind of sub-pipeline, if you will. So ZIO VDEV child IO has this thing called VDEV child pipeline, which looks like this little piece on the right-hand side. It's just the IO stages that are going to VDEV and the done callback, and that's it. So it's a very small pipeline, but it is used very heavily by all logical IOs that are trying to do IO to disks. So every time a logical IO comes in, it will actually create a VDEV child to go do this work on its behalf. The VDEV child will run through this. The logical IO will also run through these stages, but what will happen is it's simply waiting for its children to do the work on its behalf, and then doesn't actually do any real IO. So the other thing to note here is the pipeline. Notice how the start stage here is this stage VDEV IO start right shifted 1. Unlike all the other pipelines where we actually start in the open stage, this is one where we start the pipeline at VDEV IO start. So again, kind of a powerful thing for ZIO create that I can specify where I start the pipeline. So I can insert an IO in the middle. Don't highly recommend it, but you can do this. So there might be special needs that you have where you're like, I want to be able to create an IO that starts at DVA allocate because I'm doing something funky. But it has that capability. In this case, this is a convenience because we want to just simply drive through the last portion of the VDEV IO. You'll also note that we actually pass in the VDEV. So unlike the other cases where we've passed in null and we let the block pointer figure it out, at this point in time, we've already taken the block pointer, we figured out which VDEVs we're going to go do IO to, and we're simply going to go do that here. I'm going to point out this little snippet here. Has anybody ever looked at this code where if it's a leaf, offset plus VDEV label start size? Okay, so, some people. So this is something to note if you're ever trying to do a translation of, I have this IO, and this is the offset in my block pointer. I want to know where that is physically on disk. What this is doing is every time we go to disk, we are shifting and adding to that offset, I think it's 4.5 megabytes, which accounts for the ZFS label on that device. So the front label has two 512K section, another 4 meg reserved piece for the boot, so that's the 4.5 meg, and we shift everything off of it so that now offset 0 associated with the logical block pointer really is 4.5 meg in. And that's what that code is doing. And it's all handled in the pipeline. Kind of a little subtle thing if you're ever having to figure out, like, how do I map this logical block to where it might live on the physical disk. Okay, so we were going into the mirror. We went through. I was going to point out one other thing that's kind of interesting here, and that is we came into this code as a logical I/O. We're creating and ZIO no waiting VDEV IOs, VDEV child IOs right here. So we're doing the VDEV child IO, creating the child and immediately no waiting that IO, so getting it going, and then we're executing ourselves, which effectively is going to take us to the next stage of our logical I/O, which would be move us to I/O done. So this logical I/O didn't do anything, and what you can expect is the very first thing that it's going to do in I/O done, wait for children to be done. So this is how, again, that stall point and notifications are critical as they drive through the pipeline. So I showed you the first half of VDEV IO start with this funky little VDEV null. I'm now going to show you the bottom half of it, which is where it actually does most of the work. So now as it's come through, we'll call VDEV IO start again. So this time we're coming through it as a child VDEV type, not a logical VDEV type because it's moved on to done. Now I kicked off my child. The very first stage that it's going to do is called VDEV IO start. Its VDEV is not going to be null, so it's not going to go through the special case. Now it's going to drop down to here and say, based on my VDEV, go call the start ops vector for that. It's also worth noting this little QIO because I may be coming in and I call VDEV QIO, and now I'm calling into the scheduler, the IO scheduler. And the IO scheduler may come back and say, hey, it's great that you want to run, but this guy over here is the one that really should run right next. So you may come in as ZIO for VDEV mirror 1, and what you get back is a ZIO for VDEV 4. And VDEV 4 is the guy that's actually going to go execute this. So again, another kind of subtle thing here is that even though you have started the IO start, you may not be the one that's actually running and going to the next phase right away. You may end up getting queued because you're being scheduled to run later, or maybe you're aggregated to go, be part of a much larger IO. Okay, so simple case here. Let's assume we have a mirror with 2 disks. This is effectively what it would look like. We would have a logical write. It would go to mirror IO start because VDEV is null. It creates a child IO. That child IO is going to be associated with a mirror. That is going to call back into VDEV mirror IO start, where it's going to create 2 children because we have 2 disks associated with this mirror. They're also going to go to disk IO start. As time progresses, our logical IO moves to VDEV IO done. He stalls because his children aren't ready to complete. The child IO associated with the mirror also moves to VDEV IO done, and he's going to wait. He's now got to wait for the 2 disks that are doing IO to complete. So this kind of shows you how things progress through the system in a very simplistic way. Okay, I have pipeline read in here, which is much simpler, but I'm probably going to just skip to this to show a couple other examples and take questions. The one thing I will know with the pipeline, and you may not have caught this when we were first looking at all the pipelines, I showed that there's these transformation stages for writes where we compress and encrypt, but we didn't see anything for reads where we decompress and decrypt. It's because they're handled slightly differently. They're handled with transformation stacks. which are in this read, BP, and knit phase. And so in here, we will actually, you'll see that the two things that are highlighted where we actually decompress the data. If you're asking for a block to be uncompressed when you're doing the read, then we'll decompress it in the I/O pipeline and pass you back the decompressed data. It's quite possible that in the new world today, when you're using compressed arc, this doesn't get called very often because we're just simply passing back the compressed block anyway. But, so anyway, let's look at a couple examples. So I have this simple little dtrace script that shows me a pipeline based on different functions. So in this case, I was tracing all ZIOs that were being executed from debuff sync leaf and debuff sync indirect. This is where we actually do the syncing of a transaction group to disk. So a couple things to note. The first pipeline, we see in here that we've added this optional not write stage. It just so happens that when we're doing the writes on a Delphic system, we add this stage in all the time to see, can we avoid the I/O? The thing we notice is it actually went to the allocate phase, so it did not avoid the I/O. So this not write case was simply, an extra stage, really didn't do anything. If we look at this other one, I highlighted this ZIO write compress. Anyone know why we see this twice? So I mentioned stall points. Whenever we stall the pipeline, the thread that's going to come back, that's actually now waiting, gets his stage reset so that next time he gets invoked, he will start off in that exact same stage. This is a case where we stalled. This I/O actually came through, got to ZIO write compress, and said, oh, my children aren't ready for me. I'm going to go off CPU. He gets woken up second time, now 150 mics later, and now completes the rest of his pipeline stage. So here's one looking at reads. And again, much simpler. And we see a similar thing at that point. This time, we're in ZIO VDEV IO done, and we see that get invoked twice. The first time, it's the logical I/O coming through. Now he's waiting for his VDEV children to actually do the I/O on his behalf, and then he goes back on the pipeline once that I/O completes. And then this is a case where we're actually doing the ZIL code. What do we see with this pipeline? So we know the ZIL does writes. Or maybe I should say, what don't we see with this pipeline? We don't see allocations. We see checksum generate, and then it goes to ready. Let's compare that to this one, where we did compression, checksum generate, not write, DVA allocate. From this, we know that this is a rewrite pipeline stage. It doesn't have the allocation phases in it. And if we look at the second pipeline that's listed here, what can we infer from just looking at that? So this is a ZIO root pipeline, has just the interlock stages. And interestingly, again, it's stalled in ZIO done. Okay. I have glossed over a lot of stuff. And I apologize for the heaviness on this early morning for this talk. But I'm happy to answer questions. We have a minute. Yes, I can make that available to you. It needs some love. So I would love for people to scrutinize this and figure out how to use it in a better way. I started this, surprisingly, for all the years that I've been doing stuff in the ZIO pipeline, I've never really had a script as good as the ZIO trace one, and which is probably like a week old.
Take 3 questions.
Yes.
How much impact GBA throttle does on this passing time? Do you have
So how much impact does ZIO throttle have on the passing of time? Oh, total spacing time. So it's interesting that it's actually an improvement in certain scenarios, and overall probably should be negligible on the rest of the time. The reason for it is that without the throttle, and we saw this quite a bit at Delphix. Without the throttle, when you have a pool with a lot of devices that are very imbalanced, your spacing time is going to be determined by the slowest device that you're writing to. But if you have the throttle in place, the throttle is giving out work initially at one big chunk and then gives it out a little at a time when things complete. So now if you have a slow device, but a bunch of fast devices along with it, that slow device got, maybe it gets only the initial increment of work, and then the rest of the work gets dealt with by all the other devices. Your spacing time just shrunk down. So that was one of the reasons why we went to tackle that, was because we were seeing cases where you would look at 10 devices and 2 of them were busy, the rest of them were sitting idle. And it's the 2 that were busy tended to be either heavily fragmented or mostly full, and they're waiting for the last pieces of work to complete. And if you've ever monitored SPA-Sync and just did an IOStat or a ZPool IOStat, you'd see this huge ramp up of work, and we're pushing out all this IO, and then it trickles off, and then it jumps back up, and it wasn't very uniform. And that was the reason for the DVA throttle code. Yes?
George, that also help account for the possibility of big writes blocking out high priority reads or coming through during that phase as well, while trying to get in more opportune times. It's something we noticed in ZPS zero storage appliance was that large writes were built up on devices, and read would come in and be blocked behind all those writes before, and that would move a lot.
Yeah, so the question, make sure I get this right, Mark. So the question is, does that account for large writes blocking out, demand reads? So that was a problem that we solved in a slightly different way. So originally at Oracle, we had kind of a simpler scheduler. And we re-implemented that at the VDEV layer. And so now there's scheduling queues for each of the IO types. And that's where the IO priority is actually passed into the VDEV layer. So we give higher priority, even though you may have a ton of async writes coming through. We give higher priority to a demand read, and we pull off of that queue, even though it may have fewer elements than the write queue does. At Oracle, we weren't doing that. We actually had kind of a combined queue where everything got sorted in there.
Right, that makes sense, but what about the actual physical device queue depths? Do you actually then keep those queue depths smaller so you can get at those?
Oh, so the question is, what about the actual physical device queue depths? I don't think we've actually looked at that to see if the queue depths. Did you look?
We did something kind of as part of that work where we were looking at the overall write pressure. Yep. And so because we have a much better handle on that now, where there's not a lot of write pressure, we detect that by how much dirty data there is. Right. Then we can reduce the number of concurrent async write IOs that we send down to the disk. So if you aren't under heavy write pressure, then we'll only send one write from SPA-Sync at a time to each disk. And so that doesn't swamp out your demand reads as much. Okay. Then if you get under heavy write pressure, we'll ramp that up to the maximum.
Yeah, because there's a range, there's a minimum and a maximum value associated with each of the scheduling queues.
Right. Okay.
One more question. Brian, I'm going to get you next after the talk.
Do the grandfather work different with 4K physical sectors?
Does this make a difference with 4K physical sectors?
Something different about the grandfather and the ZIO?
So with regards to the pipeline, no. So the fact that we're using 4K physical sectors won't really impact the pipeline as much. It's possible that the gang code, I'd have to go back and look at this, that the gang code may not be accounting for physical sector size and may actually try to do smaller allocations than the physical sector, but I'd have to see if that's the case. So I'm not certain. That's the only place I could see where we would actually do some aspects of that. There is also in the IO pipeline, the other area is where you may have to do read, modify, writes, and you're doing sub-block IOs. So that also lives in ZIO VDEV IO start. You'll see a place where we actually have, I think it's called ZIO sub-block, where it's a case where we're doing an IO which is smaller in size than the physical sector size, and so it tries to like zero out the tail of it as part of that work. Those are the only two places I can think of in the pipeline where we would be impacted by having different physical sector sizes. All right, I'll talk to you.
Well, this is just for those watching the video. I noticed there were some observations you made or explanations that are not in the code. I assume if people want a good way to get involved with OpenZFS would be to, the comments are pretty safe as a delta.
Yes.
Adding some comments around like why we're in here, start twice and so on.
Yeah, so Brian made an observation, which is a great one, that for those in the room or even online, some of the things that I presented here, it would be great if we actually had comments in the code, going back to Brian's original tweet, that actually explain some of these things. That's a great way to get involved and be part of the community. We welcome that and we look forward to having like new members that just simply want to play around with the code. Great way to get started. All right, thank you.